All right, so 3C, never not first, direct substitution, right? We plug in, and we get secant of pi halves. Secant of pi halves, of course, everyone knows secant of pi halves is undefined, right? Because it's some type of infinity. Good. Okay. Just like yesterday. And then when you plug into the bottom, you get 1 plus tangent of pi halves. Tangent of pi halves is also undefined because it's some type of infinity. Infinity plus 1 is infinity. Now, for the indeterminate form, it doesn't matter if it's plus infinity or minus infinity. It's just quotient of two infinities. That means we can use L'Hopital's rule. So we'll give it a shot. We'll see where it leads. And the derivative of secant, of course, is secant x tangent x. And at the bottom, we get 0 plus the derivative of tangent is secant squared, also known as secant secant. So you're always going to want to simplify before you try direct substitution again, and your secants divide out. So now you try direct substitution, you get tangent of pi halves, which is infinity, over secant of pi halves, which is also infinity. Yay. So L'Hopital's rule might work if we do it again. So the derivative of tangent is secant squared, also known as secant secant, as I already said. And the derivative of secant is secant tangent, and you get that, and the secants divide out. Plug in again, you get infinity over infinity, and you can take the derivative again if you want, but hopefully at this point you realize you're caught in a loop, and you don't want to keep doing it for 27 days without sleep or food or drink, because you would only last about 11 days, okay, not 27, because I think you can only go like 10 days without sleep, 27 without food. So don't be that committed to this problem, you know, with myopic views, that you perish in your effort to make L'Hopital's rule work. So realize that you're caught in a loop, jump out of the loop, and now at some point, you can go back to the beginning if you want. You can come back up here, or you can keep it here. You don't have to go back to the beginning. Just wherever you are, or at some other point, retreat and try a different method, okay? So I'll just keep the bottom line here. One of the things that we did when we were solving proofs was put everything in terms of sine and cosine. So I wonder if that works here. That's 1 over cosine times sine over cosine. Oops, sine over cosine, sorry. And now you can either stay, change, flip, or what I like to do, right, lick them over lick them. So multiply by cosine over cosine, and then you end up with 1 over sine. And now if you use direct substitution, plugging in pi halves, you get 1 over sine of pi halves. That's 1 over 1, which is 1. If you had retreated to back up to this line, then you would end up with not 1 over sine, but sine over 1, which when you still plug in is still 1. So I would probably choose one of those two, because if you went back to the beginning, you got that pesky little term to mess with. And it's probably better just to have fewer terms. All right, any questions on that? You've seen it twice now. Oops. All right, part D. Okay, so the moral of the story here is that L'Hopital's rule, although it's a really, really good tool, it's not the only tool we have. It doesn't always give us what we desire, okay? All right, so here we got the limit as x goes to infinity. If you plug in, natural log of infinity goes to infinity, and then 2 times the square root of infinity is infinity. So this is a good candidate for L'Hopital's rule, but as we've seen in the past, if you are going to infinity or negative infinity, if it's an end behavior limit, and you have a quotient of 2 functions, you can analyze how fast the numerator grows with respect to the denominator. In programming, they call that the big O function. The big O function would be written like this, O of x. And it's basically a function that tests how fast things grow. Computer programmers do not want programs to grow very fast at all. Computers prefer to do more calculations slower and fewer calculations faster. They're less likely to crash. So if you remember this little slow to fast, if you remember this hierarchy of functions based on large values of x, the slowest growing one is a constant because it doesn't grow at all. Marginally faster are log functions. Then you got your power functions, x to the n. Then you got your exponential functions, b to the x. And then you got your aleph functions, x to the x. Now within each of those families, of course, they have their own hierarchy. So like for x to the n, x cubed grows faster than x squared. B to the x, 3 to the x grows faster than 2 to the x, so on and so forth. So we're taking a quotient of a log function to an x to the 1/2, a power function. And so which one grows faster for large x, the top or the bottom? The bottom. It grows faster, so anytime that happens, it goes to 0. So that's another way to analyze limits at infinity if you have a quotient. But let's quickly do L'Hopital's rule, because it also might work if I don't get caught in an endless loop. The numerator's derivative is 1 over x. The bottom is x to the negative 1/2. If you want to clean that up, put that over 1. There's lots of ways to do it. You can do state change flip. That's 1 over x times 1 over x to the negative 1/2. If you then add exponents in the bottom, you end up with 1 over x to the 1/2, which is the same as 1 over the square root of x. And so if it wasn't obvious to you in the beginning, now you can clearly see that the top is a 1. It's always a 1. It's always a 1. Someone just hijacked my recording. All right, we'll stop right there for now.